So moving in a new direction now, I'd like to talk about power and efficiency. To start off, let's just write out the definition of power. We're going to find out that power and work are related to one another. Power is the amount of work that an object or a system can do per unit of time. The amount of work done over a period of time. Work had nothing to do with time, right? It was force, it was distance, but it had nothing to do with time. But power relates work to time. So for instance, let's imagine that we go to the gym and we have these barbells and they're incredibly heavy, and I don't know, maybe they're like 200 pounds or something like that. Okay? Now, you and I can stand side by side and we can lift identical 200 pounds side by side. But maybe you can lift that weight a little bit faster than I can. Okay? We both lift at the exact same height, but you are able to do this a little bit faster than I can. Maybe I take 5 seconds to lift this set of barbells up. Maybe you take only 2 seconds to do it. Okay? That indicates that you have more power. That what you did was more powerful than what I just did. Power is the rate at which work is done, which is kind of sloppy language. Power is the rate at which work is done. Remember what we said early on in this semester, that anytime you hear the word rate, that is talking about on a per time basis. So work done over a unit of time is power. So if we both lift the same weight, the same distance, well, we've both done the same amount of work. But if you have done it in a shorter amount of time, then you would be more powerful than I am. Okay, just a simple thing there. Perhaps you've already seen this elsewhere. If I rearrange this, if I think about this just a little bit differently, I know that a fundamental amount of work is equal to F dot dr. This is how we define a small amount of work. We did this not too long ago. So I can plug that in to my equation for power. So power, as I said, was equal to du dt. But if I plug that in, this is just going to say F dot dr dt. Ooh, well, I know what dr dt is. That is my velocity vector. So another way for me to indicate power is to take the dot product of a force times the velocity. So if I know a force vector and I know the velocity vector, then I can dot those two vectors together and I'll get a scalar. Remember, this is called sometimes the scalar product, the dot product. In go two vectors, out comes one scalar. Power is a scalar after all. And it tells us, okay, the rate at which work is done. The units for power, okay, are going to be work per time. So for power, that would maybe be 1 Newton meter, that's work, per second. That's also equal to 1 joule per second. And 1 joule per second is known as 1 watt, capital W, watt. Okay? So if you ever see a capital W, that indicates it's a watt. 1 watt is equal to 1 joule per second. It's equal to 1 Newton meter per second. In English engineering units, of course, we do things a little bit differently here. Base unit is 1 HP, which does not stand for Hewlett-Packard. It stands for horsepower. It's an antiquated, old system of units, horsepower. 1 horsepower is equal to 550 pound force feet per second. 1 horsepower, if you need to convert into watts, is 746 watts. So depending on the system of units that you're using, here you go. The base unit for power is the watt in SI. It's horsepower in English engineering units, which is equal to 550 pound-force feet per second. And 1 horsepower is equal to 746 watts. Well, that's really all I have to say about power. Okay, it's the rate at which work is being done. We can always use this equation too, which is force dotted with velocity. Not speed, velocity. For the dot product, you must have 2 vectors going in and 1 scalar coming out. Related to power is this concept of efficiency. No system is 100% efficient. Efficiency is a ratio of useful power out to useful power going in. Ratio of power output to power input. Epsilon is equal to power out over power in. No system is 100% efficient. 100% efficient system would say that all of the power that goes into your system comes out of your system. All real machines in the real world have less than 100% efficiency. (1.0) or 100%. Sorry, just not happening that you're going to come up with a system that has 100% efficiency. Let me give you an idea. Here is a little electric motor that I'm going to draw here. And it's spinning a shaft that's connected with a pulley over here to some other device that's doing something else. Okay? So here's our electric motor. Well, how does that electric motor work to begin with? Well, you have to plug it into the wall. Okay? So if I draw a little box around my electric motor, I realize that there's power going into my system. This is called electrical power going into my system. P is equal to IV, your current times your voltage. And there's clearly power that's going out of my system because I am driving some belt over here that's driving a pulley that's doing something else, okay? So there's power going into my system, there's power going out of my system. Now in the real world, this power out value will be identical, in the ideal world I should say, the power out would be identical to the power going in. But we know that if we were to take our hand and touch the surface of this device, it's probably pretty hot. The reason why it's pretty hot is because there's friction built in there, there's electronics, there's resistances, and so forth. And this increase in heat is actually a reflection of lost energy. We also can hear this motor running. Those are pressure waves. Those are actually losses as well. That is energy. It takes energy to create sound. So there is some work, or I should say some power, that is being lost. Oh no, we'll call this P lost. Maybe it's in the form of heat. Maybe it's in the form of sound. Maybe it's in the form of friction, which are all kind of related to one another. P lost. Oh no, look at all of that. P in must be equal to P out plus P lost, because there's no way that you can create energy. There's no way that you can spontaneously destroy energy. So conservation of energy tells us that the total amount of power must remain constant within that system. And because P loss is not 0, we find out that P out, darn it, is going to be less than P in, which means that the efficiency, which is P out over P in, is going to be less than 100%. Okay? So no real system has 100% efficiency, unfortunately, no matter how well it's designed. Okay? Just you can't do it. Again, if you're going to take thermodynamics with me, we'll learn about that in some more detail. Last but not least, procedure. Remember that there is a procedure provided for you in the end of most sections of this book pertaining to that particular topic. Okay, so I get these procedures more or less from those little green tables in the end of each section. But anyway, procedure. Step 1, draw, you knew it, free body diagram to determine resultant external force acting on body in motion. Sorry, lots of words, but very important. Step 2, determine velocity of object where force is applied. You might need to know from energy principle, that's the work in energy principle, or the equation of motion, okay? In order to solve for that velocity, you might need to turn back to chapter 12 or chapter 13 or earlier in chapter 14 in order to solve for that velocity. Step 3, multiply force magnitude by component of velocity in direction of force. So P is equal to F dot V, but that's also equal to FV cosine theta based off of our definition of the dot product. So step 3 is basically saying skip to this step. If you can resolve the force in the direction of the velocity, which would be F cosine theta, and then multiply times the velocity, or you can resolve the velocity in the direction of the force, V cosine theta, and then multiply times the magnitude of the force. Sometimes you will use P is equal to du dt. So don't forget that that is also a definition for the power as well. And then step 5, input, output, power related to efficiency. P out over P in, okay? So maybe they give you the power, you solve for the power out, but they also give you the efficiency of the system. Once you solve for power out, then you can solve for power in. If it says the system is 80% efficient, and you determine from the previous steps what power out is, then it's pretty easy to solve what power in is. Or vice versa. Maybe they give you the power in to the system and the efficiency, and you need to determine the power out. That's basically step 5 is don't forget about the efficiency if they give you information about that.